electric field. We're going to introduce electric field. So let me put this here. So we're moving on from the electric force to the electric field. That's different. And we will be working with, there's a document in Canvas, and it's called Worksheet Electrostatics PDF. Right, you've worked with it before, but now we're going to be looking at pages. Let me see what pages that was. Pages 17, 18. Okay, so pages 17, 18, and 19, but it's actually labeled as page 15, the last one, so for some reason 15. So 17, 18, 19, although when you get to page 19, it'll actually be labeled as 15. Anyways, this is what you're working with. And all right, let's introduce the concept of the electric field. So what we have is a situation where, let's say you take a positive charge, let's say you take a positively charged balloon maybe. So you have a balloon, you charge it such so that it is positively charged, so we've removed some electrons, and you take another positively charged balloon. So again, you've removed some electrons, and there we have that. Now the two will repel. In fact, if you take one of the balloons and you move it towards the other, and so you take this balloon and you start moving it towards the other one will move. But that should we're kind of used to it because we've always seen it, but that should be strange, because see, this balloon here, the one that I'm moving right now, is not in contact with the other balloon, and yet as it comes closer and closer, even though it's not in contact with the other one, it's going to push it. Now normally suppose there was a block here sitting on the table, right? So there's a let's make this table a bit better. So here's the table. On the table there's a block that sits here, right? So it's some block, it has some mass m, and here's Mr. Klappik standing in front of the block. Now Mr. Klappik is not going to come into contact with the block, but without coming into contact with the block, Mr. Klappik is going to, you know, exert himself, and he's going to cause this block to move without touching the block. So here's the block, and I'm not going to touch the block at all, but I'm just going to look at it, and I'm going to, as I come closer and closer, I'm going to cause this thing to go. That's not going to happen. I can't move it unless I come in contact with it. It's just not going to happen. I cannot move anything unless I come in contact with it. Now you could say, well, maybe I could blow air out of my lungs and cause it to move. Well, in that case, what I'm doing is I'm coming in contact with the air, and then the air is coming in contact with the block. So without making contact, I cannot move this block. But what we have here in this case is a positively charged balloon that as it comes closer and closer to the second balloon, without touching it, without coming in contact with it, it's going to cause it to move. And that should puzzle you. You're used to it because you've seen it, but you never thought about it much, I suppose. But why is it that this balloon will push this one, even though they never come in contact? And that was a mystery for a while, until we introduced the concept of the field. Now something similar happens with the, you know, with the surface of the earth and the block that sits here. So if this is the earth and then you have some block or some mass here, why would this little mass move towards the big mass even though they never come in contact with each other? Like, why would that happen? So what we need to speculate about is that perhaps there's something filling up the space here between the little mass and the big mass. There's something here that transfers the energy in such a way that it pulls this thing down. Like, if there's nothing here, then that one shouldn't really move. Same thing here. If there's nothing in between the two, then this one shouldn't move. You can think of it as if there was a, so let me get rid of this question mark. if I had a spring between the two, so suppose I had a spring between the two, here's the spring, and then I take this balloon and I push it to the right, then this balloon will also go to the right. So if I push this one to the right, this will also go to the right, but that's because I have something between them. Now if there's nothing in between them, so let's get rid of this. Right, so if there's no spring between them, if there's no attachment, if they're not attached to each other, there's nothing between the two, then as I push this black here to the right, this one shouldn't go anywhere. Right, but now once we put charges on these balloons, if this black does in fact go to the right, then this one will also go to the right. So there has to be something in between them, and we speculate that, well, we're just going to call it a field because it fills up the space. We're going to make a wild guess, essentially, is that there's something between it. We don't really know what it is, but we're going to call it a field because it fills up space. And we're going to call it electric because it is due to the presence of the electric charges. So we're going to say, I'm going to draw a question mark again, but we're going to say that this is some sort of a field, and we're going to call it electric field because it is due to the electric charges. Now, a couple things about it. One is that you can't see it. You can't see the electric field. You can't smell it. You can't taste it. You can't hear it. And you can't feel it. Now you can feel the effects of it, right? But you cannot feel it itself. So it's not a subject to any of the senses that we have. But it causes effect in our senses because you can see the balloon move. You can feel the balloon move if you were attaching it. Maybe you could hear the balloon move if it was sliding across the surface. So you can perceive with your senses the effects of the presence of the electric field, but you cannot perceive the electric field with your senses. And so in a sense, it is a bit of a mystery. Now, we can, well, we can do a little more than that. We're going to speculate from the effects that there's a cause here. And the cause is going to be what we will call the electric field because it somehow has to fill up the whole space here between the two balloons. And we're going to call it electric because it is due to the charges. All right. Now, that's entirely useless if we cannot attach any math to it. So what we're going to do is keep guessing, and let's draw a few different pictures here. Let me get rid of this. So let's continue to study the effects of that field. Let's say I have a positive charge, a big positive charge. I'm going to label this as big Q. So I can study the effects of this field. There's going to be a field around it. I mean, we're going to speculate that there's a field around it. I'm going to study the effects of that field by doing the following. I'm going to take like a little charge, small q. It's very, very, very small. I'm going to place it here. Yeah, so there's a positive charge right here, but it's a small q. And I'm going to specify, I don't need that anymore. I'm going to specify here that what I have is that q is a lot bigger than little q. Now what would be the effect here? Well, the effect would be that there would be a push in this direction. Right, now suppose that I took this positive charge and I placed it here instead. Right, so I'm going to take the little q, I'm going to put it here. What would be the effect? The effect would be that there would be a push in this direction. And I'm going to continue on. I'm going to take this small q, I'm going to place it all over the place. I'm going to place it here, and I place it here, and I place it here, and I place it here, and here, and here. And then I'm going to observe the effects, because I can observe the effects. I cannot really observe the field directly itself, but I can observe the effects. I'm going to do is I'm going to draw the effect here, which is there's a push in this direction on a charge. There would be a push in this direction on this charge. There would be a push in this direction. There would be a push in this direction and in this direction. And there would be a push in this direction as well. Now, what if I took this charge, Q, and I placed it a little farther out, not equidistant from the big Q, but as to what I did here with this charge around that circle. But let's say I placed that little Q here. What would be the effect of that? Well, there would be a push in this direction, but the push would be less so. What if then I placed this positive charge here? What would be the effect? Well, the effect would be that there would be a push in this direction, but even less so. And so what I can do is I can do the same thing as before. I can take this charge and put it here. I can put it here, and put it here, and I can put it here. And I can put it a little farther out, and a little farther out, and a little farther out. And maybe I'll put one here. Where else? I guess that's it, because then I ran out of room. So I would have, at this location, I would have a push in this direction, but it would be less here than it would be here. And it would be even less here than it would be here. And the same thing, I would have a push in this direction, but it would be less here than here. And here I would have a push in this direction, but it would be less here than here. Here I would have a push in this direction, but it would be less here than here. And I would have a push in this direction, but it would be less here than here. And something similar in here and in here. Now, and of course, what would I have here? Something similar, something similar, something similar. What would I have here? Similar, similar, and similar. What would I have here? Similar, similar, and similar. So let's add these effects. I would have a push, and then smaller push, and then smaller push. I would have a push, and then smaller push, and then smaller push. I would have a push, smaller push, and then smaller push. So what I see is that the effect of the electric field is tied to the concept of the force. I perceive the electric field through seeing the force in a sense. And so we're going to speculate that we're not ready for the equation yet. Let's just focus on the drawings of this and so on. So anyways, so what I have now is I can redraw this, and let's say I take a positive charge here, and then instead of drawing a million little arrows, what I can do is I can just draw sort of a line here, that a line in this direction, and 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 here, and here, and here, and here. And I can indicate the direction of the effect of the electric field by doing this. Right, and of course, what do I have between these two lines? More lines. So if I wanted to, I could add more lines. I could put one more line in here, and I could put another line here, another one here, and 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 another one here. So we have that. All right, so this is what we'll draw for the electric field of a positive charge. We're just going to say that this is the effect we perceive, and we're going to say this is the electric field, right? So we kind of conflate the effect with the field itself, but as it turns out in the end that it kind of works. So we'll label this as electric field lines of a positive charge. And so we'll say that every single positive charge has an electric field around itself, and the electric field points away from it. That's kind of by convention about pointing away. Now suppose that I have a negative charge. Oh, actually, so while I'm here, let's take a look at this here. So in 3D, and I'm not sure how well you can, what's the resolution of this image here, but in 3D, you would have, here's a positive Q, so there's a plus in the middle, and then the electric field points in different directions away from this charge. We can't quite see the electric field, but it's there and we can perceive its effects. The effects are kind of analogous to what happens with the push on a little charge, little positive charge, if you were to place it here or here or here or here. All right, now let's go back to the picture there. And what I want to do is I want to do looking for some space. Maybe I'll move. Let's make this 33. Oh, I know what I did. Okay, well, all right. So now let's do a negative charge. So if I have a negative charge, let's do negative charge somewhere here. Right, so here's a negative charge. I'm going to call this big Q. And then let's say that I put a positive charge somewhere here, small positive charge somewhere here. What would happen to it is it would be there would be a push in this direction. And then if I placed another, I see I drew there. Okay, let me fix that, because this is I drew a plus, but this should be, I meant to draw a minus here to indicate this is negative. Oh no, this is a plus. Positive charge attracted to the negative. Okay, so it's drawn this way. And if I place a positive charge here, it's going to be drawn in this direction, small positive q. And the same thing, if I place small q here, it's going to be drawn in this direction. If I place small q here, it's going to be drawn in this direction. If I place small q here, it's going to be drawn in this direction. So what I get for the negative charge is the opposite effect, in that I'm going to get these field lines that point towards the negative charge. So I'm going to draw them, and I could add more here, and then let's do one more here. Let's preserve some symmetry. And so now what I have is electric field lines of a negative charge. So the first thing that you need to notice is that these here would be, we have now electric field lines for a negative charge, and we have electric field lines for positive charge. I need to know how to do the two. Now from here, and also from the positive, they always point away. For the negative, they always point towards it. All right, now let's figure out, so we know how to draw the electric field lines for positive charge. Let me do that. Here's the electric field for the negative charge. Then we do it on this side. Here's negative charge. And then let's draw like, so this is towards, and towards. And then here's the electric field for a positive charge. And we have here, this one points away, away, and away. I suppose I should add a few more of these lines. And of course you have infinitely many lines between these lines, but you draw only a few to indicate sort of the shape of the electric field. Now what would you do if you had instead, so these are two, there's a positive charge here, there's a negative charge here, but they're individual charges and they're separated. What if you had two that were close enough to interact with each other? So suppose you had a positive charge here, and then you had a negative charge here. How would the electric field between them look like? So you do something very similar as what we did before. You take a small positive charge and you place it somewhere in kind of guess which way it would go. And there's a bit of a lie in the process here, but it works in the end. So we can use it. Let's say you place a positive charge here, like right at this location. Which way would it go? Well, it would move away, but it wouldn't just move away in a straight line, because while it's moving away from the positive, right? This little dot here, little dot is the same thing as the positive. That this thing is just a positively charged small q. So if you were to place this little positively charged positive charge here, it would move away, but it wouldn't move away linearly because it would also be attracted to the negative. So really it would take kind of a path that would look like this. It would be a curved path. This would be the path it would take. Now if you were to place this positive charge somewhere here, it would do something similar. It would move away, but it would move away along the curved path and eventually would come around and go to the negative. So you'd have, this would be the path it would take. If you were to take a positively charged particle and place it right here, it would move in a straight line to the negative. Now let's do maybe one here. So suppose you place positive charge here and then here, and we'll do one here, here and here, and that should give us a picture of what the field looks like. So you would then have that this particle would move like this and then come around. This particle here would move like this and come around. And then here, if this was the particle, it would move away, but it wouldn't move away linearly because there would be some pull from the negative. So what you would get is something like, you'd get something like this. And then this particle would do something similar. It would move away, but not linearly. It would curve because of the presence of the negative. And then finally, if you had this particle here, this would just move linearly away. All right, and then on the other side, suppose you had a particle here. Let's put it like here. What would it do? It would move towards, this is a positively charged particle. It would move towards the negative, but it wouldn't move towards it in a linear fashion because of the repulsion from the big plus. So it would curve like that. And then if you were to place a same thing, another one here, it would move along a curved path. And if you place positive here, it would move towards the negative in linear fashion. So this would be the electric field that you could figure out for the positive and negative. Well, I'll do one more. I'll do plus and plus. So let's do plus and plus here. You have a positively charged particle and a positively charged particle. How would the electric field look like between them? Well, you do the same thing. That is, you take a small q and you place it somewhere, small positive q. You place it in different locations and try to figure out what path it would take. So let's say you place small q here. small positively charged particle here, what does it do? It would move away, but not in a linear fashion because of the presence of the other q. It would curve. It would do something like this. Right. If you were to place the particle here, small plus here, what it would do is it would curve away like that. Right, because of the presence of that one. Now, if you were to place a charged particle here, what it would do is it would curve away like that, and another one would curve away like that. If you were to place another one here, that would just move away in a linear fashion, right? So there's that. Now, suppose you were to place a positively charged particle here, what it would do is it would go like this, and a positively charged particle here, it would go like this. I should have kept the symmetry. Let me see if I can make the second one a little better. This one here. So it would go like that, and then if I were to place another particle here, it would move like this. Another particle here would move like this, and then maybe I'll do one here. It would just go out like that, right? I should probably add something here, add something here, and I'm gonna add something here, and add something here. So there's your electric field for a plus and plus, and then you could figure out something similar for a minus and minus. If you were to do minus and minus, let's do maybe minus and minus here. And the electric field in that case, which you would do is, it would actually be the same as, well, let's try it. So if you were to place a positively charged particle maybe here, it would move towards this one because it's closer, but it would be attracted by that. So it would follow a curved path like this and would just go towards it. If we were to place positively charged particle here, what it would do is it would move towards this one because it's closer, but it would be attracted by that. So it would follow a curved path like this. I should have done a better curve. And then you would get something similar here. You would get something similar here. And then you'd get something like this here, something like this here, and then another line there. And then, you know, I'll do the other side as well. So we get that as the effect, and then maybe I'll add something here. All right, so here's the electric field of a minus and minus. And then of course you could get the electric field of all sorts of different combinations of charges. So maybe you would have like a plus, plus, and minus. And what does the electric field look like, and so on. So what I'm going to show you now is somewhere here I have pictures or images of the electric field. There we go. So this is for a charged particle. I showed you that already. This would be for a negatively charged particle. All right, so this here, that's a negatively charged particle at the center. This here is a positively charged particle at the center, and sometimes we will draw electric field like this with the arrows that change change at different locations, and sometimes we will draw electric field just by lines. So we in this class will simply do lines for the most part. All right, so in here we would just draw a line like this and a line like this and a line like this and so on. Here these lines would be going towards the negative charge, but you can also represent electric field just by doing this. This is more accurate, actually, more accurate in the sense that it conveys a little more information because you have the size of the electric field at different locations. Here you don't really have that, but here's an electric field. This is stolen from MIT. They have something posted about the shapes of the electric field. So here what we have is it's difficult to say which charge is positive, which is negative, but it indicates to you, it shows you the, so here's a plus, and then here's a minus. The difference between the two though is that this is a much bigger Q and this is a much smaller Q. So you have a big positive charge Q, and then you have a small charge Q, and that has an effect on the electric field as well. Now, it might actually be that this is a negative and that's a positive, but the shape wouldn't change. It's just that the direction of the lines would change. There's no direction of the line, so we can't tell which charge is which. Here's another one. Let's say that you have, so you have a big Q. I'm going to call this positive Q, big Q, and then there's a small Q somewhere here. So you have little Q. So there's like a much smaller charge, positive charge. These are the same charges. So you have a smaller charge somewhere here. There, smaller charge, bigger charge, and then the electric field would look like that. Here's another one. So this is essentially, this one here is essentially the same as this one. It's just one is vertical, one is horizontal, but so you'd have some kind of a big charge here. Right, I'm gonna put big plus, and there's a small plus right here. And I think this is all I have for the images. Okay, all right, so there's that. So these are the electric fields you can sort. There's always electric field filling up some space. There's not, between the lines, there are more lines, infinitely many more lines. So this is more like a space itself. That's wrong. You shouldn't say that. but it fills up all of space. The electric field fills up all of space. All right, so now that we have some idea of the electric field, I'm gonna have you work with the worksheet. So you should pause this video, and then in the worksheet, what was that worksheet? It was electrostatics. There. Worksheet electrostatics PDF. It's on your canvas. Do pages. Let me think. I think it's 18 and 19. These two. The ones where you have only the drawings that you're dealing with the drawings of the electric field, but you're not calculating anything yet. Let me double check that. And it's a good thing I did check it, because it's not 18 and 19, it's 17 and 18. And actually the pages for some odd reason work out. So do pages 17 and 18. This is just drawings of the electric field. Right, so do pages 17 and 18, and then don't do page 19 yet. Now you have the answer key too. So do these pages 17 and 18 first, and then you can, once you're done with that, you can check the answer key and see if you got it right. Right, and then what I want you to do is, once you're done with pages 17 and 18, you've checked the answer key and you've corrected your errors, unless you've got everything right, then you can come back to this presentation, and we'll look at, I'm always wondering if we even should, because I probably should. Well, let me introduce the next thing, which is going to be related to page 19. So let me introduce the next thing, and then we'll probably just pick up with it next time I see you. It would be good to have a continuum here. So what I'm going to do is I'm going to steal this idea that we had, where we have this positive charge, and then we place a small q. So there's a big q, big q here, and then we take a small little q, and we place this small little q somewhere out here, and then we observe the effect, and the effect is that this q is pushed in this direction. And then we do the same thing. We put this little q here, and it is pushed in this direction. We put this little q here, it is pushed in this direction. And let me just redraw it. And so we get that. And of course, as you move farther away, you get less of a push, less of a push, less of a push, and so on. Right, and then maybe I'll do one more. So there's like even less here, less, less, and less. And of course, we have more of these lines, more of these electric field lines in between. Now, what we want to do is we want to determine an expression for the electric field itself. So we're going to guess this by, well, so there's a certain distance between big Q and little q. I'll label this here as distance. Do I use R? I think I use R. Let me use R. Or D. I don't know what your worksheet uses. Let me use D. I have a feeling that your worksheet uses D. So there's a distance between big Q and a little q. And we know the equation for the electric force. Right? The equation for the electric force between big Q and little q is just K big Q times little q over D squared. So when we do all of this stuff here, when we're trying to figure out the shape of the electric field, we place this little q. But this little q is irrelevant, right? You remove the little q, and you should still have the field present, or so the assumption goes, that you should still have the field present in this at this location here. So we're going to do something very similar, in that we're going to take this equation and we're going to get rid of the little q, and that's going to give us an expression for the electric field. So the electric field is going to be K big Q over D squared. Now this is a pure guess, but as it turns out, it works, and it works very, very well. So from now on, if you have a charge, whether positive or negative makes no difference, but if you have a charge, let's say plus, and you want to figure out, and this is Q, big Q, and you want to figure out what the electric field is, let's say here, at this location, and you know it's going to point away. E. You want to figure out what it is, then what you need is the big Q, and you need this distance to your point of interest. So you're going to need this distance here, distance D, and that's all you need. As long as you have D, as long as you have Q, you can figure out the electric field here. If it's a positive charge, then electric field points away. If it's a negative charge, let me do that. So if you have a negative charge and big Q, and you want to figure out what the electric field is at, say, this location here, due to this charge, then you would have, well, you need big Q, you need the distance from big Q to the point of interest. So you need this distance D. And then of course the electric field, because this is a negative charge, would point towards it. All right, so for a negative charge, electric field points towards it. For positive charge, electric field points away from it. Here's the equation. Now page 19 works with this equation, but I think we can probably stop here for today, and then next time we see each other, we'll pick up with page 19.